Thank you, everybody, for joining our Innovation Hub webinar series here from CTS Piezoceramics. First, I'll say that we are part of the CTS family, which is a leading manufacturer of designing and manufacturing custom engineered solution that sense, connect, and move. And we have sites in both the US, Europe, and Asia. And this is the plan for the different for the webinar installments. So we are currently at webinar number 2, Piezoelectric Actuators Application Design and Performance. And the Innovation Hub initiatives is about bringing ideas to life. So an idea can start from many places. It could maybe be this webinar or other. Then you need to evaluate your idea. And here at the FEOPAM, we offer some free services to help you with that. That could be free samples, finite element modeling, characterization, or a small feasibility study. Then if you move on, you move to the proof of concept. And in this stage, we have customer ordered projects where we can design and evaluate together on prototypes. Then from that, you go on to pilot production, full-scale production, and entering the market. So for the services we provide, we offer characterization of materials. We have a full spectrum of measurements, also climatic measurements. As this webinar is part of workshop webinars and trainings that we offer. And then also modeling services and free samples to the sizes you need. And then for the customer orders project, we can help with the design and specification, or to make an optimal solution, or to manufacture the first prototypes for proof of concept evaluation. So new ideas may require completely different and customized solutions, and we can try to help you with that. And if you have any inquiries, you're very welcome to contact us at dk.innovation@ctscorp.com. And then I think we are ready for the Actuator webinar, which is hosted by Charles Monchot, who is the Piezo product manager at CTS. And he has more than 20 years of experience within the world of piezos. So with this, oh, and I should say, you're very welcome to post questions as we go along. I'll keep an eye on the Q&A and the chat function. So please do that if you have anything. So now it's ready for you, Charles.
Great. Well, thank you, Louise, for the introduction. Let me just switch to my screen. And thank you, everybody, for attending. Also, if you are looking at this webinar afterwards, because this is recorded, so it will be accessible on our website. Right, so as you mentioned, I will talk today about piezoelectric actuators. And the topics that I will cover will be just an introduction. What is piezo actuation? Applications, the behavior of piezoelectric actuators, which is very important to understand for designing an application, and then details about design, performance, what are the important parameters, how should an application be developed, whether it's a quasi-static or a dynamic application, and then some conclusions. And again, as Louise mentioned, please don't hesitate to ask any questions as we go through this webinar. All right, so piezoelectric actuation, what do we mean by actuation? We use the converse piezo effect. So if you've attended one of our previous webinars, you're familiar with that. This is the relationship between an electrical field and mechanical strain. So by applying an electrical field, we generate a strain or a displacement or a force or a combination of those. So when we talk about actuators at CTS, we are considering components that generate motion. And when we say motion, this is motion that is not at a mechanical resonance, or not only. So it's motion over maybe a wide frequency range, but it's a controllable motion. It's not just a vibration like you would generate, for example, with the transducer. There's also the distinction between actuators and motors, and you will find different definitions in the literature. What we consider an actuator here is something that can generate a position or control a position or in a continuous way. And typically an actuator will return to its original position if power is removed, whereas a motor relies on performing multiple cycles with an actuator. Typically a motor will have unlimited range, so you have rotary motors, for example, or linear motors. Obviously linear motors have a limited range, but that can be extended without changing the actuator. And you could think of it like the analogy with electromagnetic, where you have a coil. A coil would be an actuator for us. So it has a limited range of motion. And if you remove power, the actuator will return to a neutral position. Whereas a motor, so a brushless motor, for example, the position of the motor is defined by the cycles that you've performed with the different coils. So this is what we consider the difference between actuators and motors. So here we're going to focus on actuators. And why are piezoelectric actuators interesting to the industry? Well, they are appreciated for the high force generation. We have a system that is very stiff, and I will come back to that. And that can provide a very fast response. So whenever there is a fast motion required, then very often a piezo actuator will provide a better solution. They also provide unlimited resolution. It's an analog element. So the resolution of the actuator is driven by the resolution of your power supply, basically. Low power consumption is also an advantage compared to an electromagnetic solution where you have to maintain a current to maintain position. An actuator will just, or a piezo actuator will just require to be charged and discharged, and it won't draw any power for maintaining a position. Also, we have no wear and tear. There are no moving parts relative to each other. Obviously, we are changing the shape of the actuator, but there is no friction, which means we can have a very long lifetime for the parts. We're talking about billions of cycles without any change in properties. And finally, the last three aspects are quite important, especially for scientific applications. We have a product that can operate in very harsh environment. We're talking magnetic fields, for example. The piezo is non-magnetic, so it can be used in an environment where there's a high magnetic field, but also it doesn't generate any magnetic field. So it can be used in experiments that are very sensitive to magnetic field. It can be used at cryogenic temperatures down to some millikelvins. And it can be used in vacuum and clean room. Again, due to the fact that there is no moving part, no wear, and no generation of particles. All right, so these are some of the, I would say, main advantages. Now I'm going to describe some applications where these advantages are being exploited. So in the industrial world, to start with, I would say the main application for actuators is nanopositioning. So nanopositioning is when you use the actuator for short range motion. And when I say short, that is somewhere between a few microns to a few hundred microns. And this is used typically in microscopy applications. particularly scanning probe microscopy. So when you have a single probe that is measuring at a point, and then you have to move your sample in a XY raster movement to cover the whole surface that you want to image. And you can find stages that can cover, again, down to a few microns, up to 200, 500 microns. This is also used for semiconductor industry for wafer and mask positioning. So whenever you have to move something precisely, then nano positioning is used. Micro positioning is when you have typically a motor. So in that case, there will be a step size in the micrometer range typically, and you use the piezo in positioning stages that don't require a very smooth and accurate motion. So these are used for positioning optics, for example, or for microfabrication, micro grippers, and that type of application. We also have actuators in dispensing applications. So by driving the piezo very precisely, you can define very precise amounts of liquids or fluids to be dispensed. So that is applied in drop-on-demand inkjet printers, but not just ink. It can be other substances such as epoxies or other adhesives or cover layers for chip assembly. So very tiny pieces that need to be assembled together and very small amounts of liquids that need to be dispensed. Another field of application is vibration damping, because we have a product that is very stiff and controllable. We can compensate for vibrations, and this is used in many different fields. One of the most important ones is semiconductor. If you're doing UV lithography, you need to be able to control the position down to a few nanometers. And that means if you have a machine sitting on the shop floor, it needs to be isolated very, very precisely. And here there's a number of devices that are used, and typically a piezo is included in the last stage just to absorb the last few nanometers. Other applications include wire bonding and test and measurements application, such as microindentation. In the medical field, we have applications in implantable devices. For example, bone conduction hearing aid. So to treat some hearing impairments where you, for example, have hearing only on one side. So it is, I mean, you have all the functions to be able to hear, but there is just this last bit missing. Then you can use a piezo device that's vibrating the skull, generating a wave that can be sensed on the other side, for example. Also, valves for drug delivery using a bending piezo actuator. Typically, you can open a valve for typically morphine injection on demand with a very controllable volume. All right. Other applications include medical pumps, or pumps in medical equipment, or instrumentation such as microfluidics. When you're doing performing tests at a small scale and you want to control how the fluid is flowing through the micro channels, then piezos can be used both as pumps or valves. Some other applications, I've put optics all together. There's a lot of different applications for optics. It can be for communication, it can be for science experiments, it can be for industrial applications, where you have, whenever you have a laser, something that needs to be positioned precisely, positioning optics, spectroscopy or interferometry, for example, where you have to position mirrors relative to each other down to a few nanometers, then piezo is used. We have a lot of applications with, for example, Fabry-Perot interferometers You see this example here where you can control the distance between two fiber optics and the surfaces of the fiber optics as used to generate this fabric barrier interferometer. So you can tune or adjust the distance to tune the wavelength that that will resonate. All right. Otherwise, shutters. That's also a very interesting application. If you need to, well, turn on or off a source, then you use a shutter, and piezoelectric actuators can provide the fastest response, mechanical response. So you just need to bring two surfaces in contact over a very short stroke, and this is a perfect application for a piezo actuator. Image stabilization is also interesting. That goes back to stabilizing or absorbing vibration, and it's used, for example, in defense applications. If you have an imaging device on a helicopter, for example, and it has to be able to see very far away, then it needs to be stabilized very precisely. Some other applications are a little bit more exotic applications, I would say. Of course, we have automotive applications, mobility, with piezo valves for seat adjustment, and some noise cancellation or noise control, vibration control applications. But there's a vast field of, well, more specific applications, such as in space. We have micro thrusters powered by piezo actuators. This is an example here with a piezo stack that is embedded into a device here, and that opens a small valve. And by controlling exactly the amount of gas that is released through this valve, you can adjust the position of a satellite. We have IT applications, hard disk drives, for example, where you have, it's again a vibration compensation or vibration control application, where when you move the read head, it has to move very fast, obviously, and you don't want it to vibrate when it gets into position. So you want to absorb this vibration and be able to position it exactly at the location that's interesting for you. And here you use piezo actuators to control, to generate some bending on the device, on the read head, and adjust position. And you might say, well, I don't have any hard disk drive in my computer anymore. Yes, definitely. But everything that you store on the cloud is saved on a hard disk somewhere. So there are farms filled with hard disks, and I can tell you that there's still a lot of hard disks produced at the moment. Right. Haptic feedback is also an interesting field for consumer applications, typically. And otherwise, at the other end of the spectrum, we have a lot of science applications, adaptive optics, whether it's for astronomy or for experiments, like in the LIGO experiment for measuring gravitational waves, which is basically a large interferometer. We have piezo actuators to control the resonant cavity of the interferometer, right? Particle accelerators are also users of piezo elements for tuning. Here it's the same idea, but it's a resonant cavity made with a superconductor that needs to be adjusted in length very precisely and very rapidly, because each time there is a beam going through the accelerator, it heats up the cavity, and that creates an expansion, thermal expansion, and that needs to be compensated. Otherwise, you're not tuned anymore. So we have a piezo actuator that reacts in the microsecond time frame to correct the dimension. And crystal collimator is also a funny one, but I will just move on and talk about the behavior of these piezo actuators. So going more into the practical details. Right, so if you've seen the last webinar by Erling and Nikolai, you will probably know, and you hopefully you know in advance, that we have a linear piezo model that has been developed, and it's based on the fact that the piezo is an elastic material, just like most materials. So when you apply a stress, it will react to that stress. But in addition, we have a piezo effect that generates some additional strain. So this is another term in the equation here. So we have the elastic part, and then we have the piezo part. This is similar to thermal expansion, if you like. So thermal expansion, you still have the elastic part, right? So your part is still elastic, but on top of that, you have a term that adds strain generated by temperature. So it's the factor multiplied by temperature. Here it's a factor multiplied by field. So it is the same kind of idea. And in the past, before the FEM simulation was equipped with piezo modules, people were actually using thermal expansion to model the piezo effect. And I've done that a couple of times. It actually works fine, mostly if it's isotropic. These equations are valid for all actuator types. Sorry.
Charles, you got a question also from
Yep.
bit of the earlier. So it's a run that asks you show clean environments. What about harsh environments like greasy automotive industry? So I think it was to one of the previous slides.
Yeah. Well, the piezo can take some, I would say, some harsh environment, but it's somewhat limited, right? Because we have a device that is submitted to an electrical field, so there is voltage applied. You want to avoid any electrochemical reaction. So it depends really what environment we're talking about. If it's low levels of humidity, then it's generally okay. If it's contaminant, then it can be problematic. If it's clean oil is actually very good because it helps with the thermal conduction. But it doesn't affect the electrochemical degradation. So it's really a case by case. If it's a contaminated environment, if it's very high humidity, for example, then I would recommend encapsulation, which is also something I'm going to mention in the actuator designs a little bit further down.
Thank you.
Sure. Right, so last point about these equations is that this is valid for all actuator types. So if you only focus on one line in these matrix equations, you will see that it is all the same, whether you're using a G33 mode actuator or G31 mode actuator or G15 mode actuator. It's always an elastic part plus a piezo effect part. And that is important to understand because, sorry, if you look at a force displacement diagram, you start from an elastic behavior here. So if you're at constant voltage, the piezo term is 0, and you have just an elastic behavior here. So when you press, you generate a displacement. Well, you know, the material contracts if you press on it. Now, the interesting thing about piezo is that if you change the voltage, if you increase the voltage to the maximum rated voltage, then you will be able to offset that curve. And this is what happens here. So if you go to the maximum voltage, you, well, generate a displacement basically. But overall, the part is still elastic, right? Constant voltage, the part is still elastic. That means you're on this top line, and in between the two lines, this is where you can actually use the actuator. As a standard in the industry, we define two values. Up here, we have the free stroke. So this is the vertical distance between the two lines. That means the displacement that you can achieve if there is no change in force. So we call it here Fs or delta L max. And the other dimension is the blocking force. The blocking force is completely the opposite. It's still distance between the two curves, but in the force direction. And there's an important thing to notice here. Blocking force is not the maximum force that the actuator can tolerate. It's just a dimension that we define to model the actuator. So if some actuators, you won't be able to apply the blocking force. It will be limited to maybe half of the blocking force. Some you can apply more than the blocking force. It's actuator specific. So the blocking force is not a limit for the force that can be applied on the actuator. It's just a way of defining these two curves, really. And this is very essential to understand. And if you look at these curves, you realize that, well, you can offset the characteristic of the piezo. That's good. But in the end, it is the load that defines the position in the force displacement diagram. So if you have a variable load, you will have a variable position, unless you have a feedback system, of course. And that points to really the essential part here for designing an actuator. You have to characterize your load in a proper way. So on a force versus position diagram, you have to know the extreme load cases. You have to know if there is a dynamic force. Here are just some examples here. If you have a mass, so if you say my load is just a mass, then it's a constant force, whatever the displacement. If your load is elastic, so if it's another material that you're trying to compress, then it will tend to be more, well, elastic. So with a linear characteristic like that. If you are opening a valve, for example, you will have a more complex characteristic, such as this one, which is flat in the beginning. Nothing's happening until the valve starts to open, and then you start to have some flow. And when you reach the maximum flow, you reach the maximum displacement, and then you start to have a decrease again. So this is really essential because the load is going to define exactly where you will be on the force versus displacement diagram. So I'm going to go through just a few examples, typical examples here, just to illustrate. So if I plot here just a triangle that goes between the origin, the free displacement, and the blocking force here, that corresponds to an actuator that has a certain length and a certain position, original position. If the actuator is completely free, you go from the 0 volts to maximum voltage, so you apply voltage, then obviously it's not going to generate any force, so it's going to move along the vertical here on that diagram, and it's going to go all the way to the maximum displacement. So if you plot it against the voltage, you start from here at 0 volts, and you go up to the free displacement at the nominal voltage. So this is very, very easy, hopefully. So now let's see some more complex cases. If you have a constant load, what's going to happen is that when you apply your load on the actuator, initially the actuator is at 0 volt. You apply the load. What's going to happen is that you will compress the actuator. This is what happens here. So the actuator moves back. Obviously, you're putting a load on it. And then when you apply the nominal voltage, the actuator will try to go to the upper curve of the characteristic. And what's going to happen is this. So it will just go up at a constant force. And you realize here that in that model, that linear model, the actuator actually moves with the free displacement, right? So you generate the free displacement. And that can be a little bit tricky to understand or counterintuitive in some cases. When you have a load, whatever the load, initially in the linear approach, whatever the load, the displacement, you will be able to move it with the free displacement. Right. On the other hand, if you have a spring load, the spring has a certain stiffness. So it has a certain characteristic. And as you increase the voltage, you will have to follow that characteristic and ultimately get to the the top characteristic of the piezo. So what's happening is that on the force displacement diagram, you increase the force as you increase the displacement. And the result is that you get a displacement that is lower than the blocking force, lower than the free displacement, and a combination with some force that is obviously lower than the blocking force. Right, so basically the actuator can provide either the free displacement, so a change in position equivalent to the free displacement, or the blocking force if it's completely blocked, or a combination. So in many cases, it will be a combination, so you will need some force, and you won't get the full free displacement. And this is why it's very important to characterize your load precisely, because you need to know and make sure that you will be able to move your load by the amount that you require. All right. Now we've talked about this linear model. It's a very simple approach. I just want to make it a little bit more complicated and try to introduce or start to introduce some nonlinear effects, because obviously nothing is perfect in our world, so we have to take into account some nonlinearity. The most significant one, I would say, is hysteresis. So hysteresis means that here on a field versus strain, or on a voltage versus displacement diagram, the piezo will not follow the same path on the way up and on the way down. So there will be a difference here, and it's material dependent. And it means that there will be some thickness to the curve here, especially in the middle. It's thickest in the middle, and can be, depending on the material, 10 to 20% of the full stroke. And another thing that I want to mention here is that with actuators, we're normally working with large signal. So we're applying very high field. On a multi-layer actuator, we apply 2 to 3 kilovolts per millimeter. Whereas the D coefficients, they are typically measured at very low field. So 1 volt across 1 millimeter, typically. And this is how they are defined. So if you look at a data sheet for a material, you will see the D33 value, which is measured for small signal, or the D15. I mean, all the coefficients are measured with the small signal. And it might not be straightforward related to the displacement that the actuator provides. So you can see here, for example, the D33 is small signal. So it's basically the slope of the curve around the origin here. And you can see for some of the materials that they are increasing significantly, or the response is increasing significantly with the field. This is how you get larger displacement than what you would normally calculate from the D coefficients. So I would always recommend to refer to the data sheets for an actuator. We have experimental values. We have experience with designing the actuators. And obviously, what we specify is for large signal. So that could be tricky if you're doing simulation, for example. But if you're designing an application based on the extreme characteristics, then please refer to the specifications rather than the D coefficients from the material spec.
Charles, there's a question here. So how strain percentage is calculated with respect to applied field?
Strain here?
How the strain percentage, yes, it's calculated with respect to the applied field.
Yes, so I should have mentioned here, this is an example for a D33 actuator. So it's a stack actuator. We made some of our regular stack actuators, and then measured the displacement in microns, divided that by the amount of the height of active material in the actuator. So we have this is typically on 20 millimeters actuator. There's probably about 15 millimeters that is active material, and if the strain is 15 microns, then if the displacement is 15 microns, then we calculate the strain equal to these 15 microns divided by the 15 millimeters active material of the stack. Right, and the field strength is actually, well, it's not something that you have access to in many cases for the actuator, because we designed the actuators with a certain internal layer thickness, and that defines the field strength. So the voltage applied divided by the internal layer thickness. We normally run our multi-layer actuators up to 3 kilovolts per millimeter. I know some manufacturers use 2.5. It's also possible to go above that. We've had applications up to 6 kilovolts per millimeter. It's possible. And obviously you get more strain, but you're also putting more stress on the material. So strain here in percent is interesting from a material perspective. If you're designing a new application, it gives you an idea of how thick the material will have to be to generate the displacement that you need. And this is in free conditions, of course. But from a practical perspective, you can always refer to the displacement values in the data sheet. So if you're using a standard product, for example, just look at the displacement, which is typically in the micron range for something that is a few millimeters thick. And I will actually go back to that when I go through the different types of actuators. Right. Just a few more words about hysteresis. We've seen the curve with the extreme. So if you go all the way up to the maximum voltage and back to 0, this is an example of a curve where we actually stopped on the way up. So we went up here. That's path C, stopped at 2 kV per millimeter, and then decreased to 1 kV per millimeter, and then increased again to 1.5. It's just to give you an idea. Actually, the scale is weird, so it's just to give you an idea about the response. So if you are moving up and down, increasing the voltage, not going to the extremes, then all you can say is that you will be inside this hysteresis loop, but it can be difficult to find out exactly where you are in the loop. And you will also see that the slope here, so the response of the piezo changes depending on the history of the sample.
And Charles, here's a follow-up question. Is it frequency dependent also? Yes,
it is. I have that's actually on the next slide, I think. So I'll just come back to that. Right. So the slope varies, and that means it can give you some challenges for driving the part. So it won't have a homogeneous response to an electrical input. In certain cases, you will need an external sensor. If you need to have an actual position that is accurate, you can have a sensor that is part of the application. So in a laser application, you may want to maximize the output. So you have directly a photodetector that gives you a feedback information. Or it can also be model-based, because this behavior here can be modeled with the mathematical approach. So it can provide you with a first, at least a first linearization. And here we talk about time dependency. So that's also related to frequency. We have the creep effect, which means that the actuator will have a part of the response will be slow over time. And it says here it applies to low dynamic applications. It does also apply to fast application, but it's easier to illustrate here for slow application. So when you apply the maximum voltage, you start from 0, you get to your nominal position. Here we assumed that the nominal position was reached after 1 second. And then if you maintain the voltage, the actuator will continue to expand. This is a little bit similar to what you see on polymers. So if you load a polymer with a certain stress, it will expand because it's elastic, but then over time it will expand more and more. And this is also called the creep effect. That's by analogy. If you zoom in on that section here, you see that we reach the position at 1 second, and then over time we have an increase. And this is actually logarithmic. So you can model it with a very simple model where the increase is between 2 and 6% per decade. You can see it's different for different materials. And that means basically if you have a creep effect of 2% per decade and an actuator that gives 1 micron of displacement, you actuate it, it gives you the 1 micron, but then 10 seconds later, it will be at 1.02. And then 100 seconds later, it will be at 1.04 and so on. So you add up to the displacement over time.
Charles, there's a question. Oh, sorry, there's a question here as well. Do you increase the voltage until failure to test the piezos? And if so, where do you see failure?
Right. Let me just cover the frequency question and then I'll go back to the increased voltage.
Yeah, okay, sorry, I was...
No, that's okay, no problem. Right, so in terms of frequency, what I wanted to say is that if you're performing cycles at for example, very low frequency, you will see that the material has time to gain some creep effect. So first of all, you will see that the hysteresis curve is shifting a little bit because there's an average voltage which is not 0, so it will tend to shift the curve, and also some of this creep response is happening over time, so it will have an impact on the shape of the curve. And the same goes if you go very fast. So if you have very fast hysteresis loops, then a part of the material will not have time to react. So the curve will tend to look more round. And if you do it really, really fast, then you might also have some dynamic effect that comes into play, so that the material maybe doesn't have time physically to move in the way that you expect it to. So basically the curve gets more round as you increase the frequency. I hope that answers the the frequency question.
Yes, yeah, you're getting a lot of questions here. So
perfect.
There's also a follow-up question on the frequency. So maybe that fits with what you just, so maybe we should take that first, but just says, may we plot displacement versus time curve from PE loop data?
Yes, well, it's possible. It's not great. So there are some models where you will see the displacement or the strain expressed as a function of charge, and it's typically with the remnant charge plus the additional charge squared, and then there's a factor. So there are some research about that and some papers. It works to a certain extent. You need to take into account the remnant, the pooling charge, basically, because the device will have a tendency to have a quadratic response to charge, but then as you discharge, it keeps some remnant pooling initially at the pooling stage. So you may not have all the information from a manufacturer, for example. But yes, there are some models to calculate displacement from charge. So if you have a brand new material and you just use it for the first time and measure displacement and charge at the same time, you might be able to get a relatively good fit between the two.
Okay. Yes, thank you. Do you want the other question now as well?
Well, I can talk about the voltage, right? So
do you increase the voltage until failure to test the piezos? And if so, where do you see failure?
Yes. So we do run tests in development stages when we design a new piezo element to see how much stress can be applied. When we do our multilayer, we have the active material that is surrounded by inactive material, and as we use it, we expand, we generate a strain of the active material, and that generates stress, tensile stress in the inactive material. So typically what will happen is that above a certain level, we'll start to damage the insulation, so create cracks in the inactive part, and that causes the actuator to fail. And this is well, it happens quite fast, right? It's not a fatigue. The material doesn't have that much fatigue. So if it cracks, right? And that means on a typical actuator like NAC 2013, for example, we test around 9 to 15, 9 to 12, sorry, 9 to 12 kilovolts per millimeter. That means 3 to 4 times the nominal voltage can be applied before the actuator just breaks itself. So there is a decent margin in terms of voltage on a multi-layer actuator. If you're using bulk, so single layer devices, then the limit will be much lower than that, because normally what happens is that you will have sparks on the surface of the actuator. I will go back to, if I have time, I will go back to the construction of the different types of actuators.
Thank you.
All right, excellent. I think I'll spend a little bit less time on those slides to be able to focus on the important part, which is coming up afterwards. Temperature behavior is also well, vastly studied. We have variation of the parameters. So you can see here, for example, the increase in relative displacement according to temperature. So at 120 degrees, for example, you get 25% more displacement. But at the same time, you also have 60% higher capacitance. So there are some, obviously, some influence of temperature on the performance, which are documented in some papers. There is a note here to reference the data. And there is also, obviously, thermal expansion. The funny thing about thermal expansion of piezo actuators is that it varies. It's not just a constant coefficient. And this is because over a certain temperature range, we will gain or lose polarization on the part. So it might actually contract. In that case, our most popular material in C51 will contract as you increase the temperature, and that's in D33 mode. So for, I would say, the most common actuator type. And obviously you need to take that, or at least to be aware of that, if you're designing an application that has to operate over a wide temperature range. Right, bulk or multi-layer, I just touched briefly the topic. We have a material, ceramic material, that we can process either by through a bulk process where we just press the material, press powder to make a single solid, or a tape cast method where we make thin layers of tape that we alternate with electrodes. So a bulk component will have electrodes on top and bottom, and these are the electrodes that you see that apply the electrical field on the actuator. So this means the field is somewhat limited. You cannot apply too high field, otherwise you will have sparks on the edges. And also the active material is exposed to the environment. Whereas on a multi-layer, the field is actually applied by the internal electrodes. The external electrodes that are on the actuator, that are visible, are only here to interconnect all the internal electrodes. So you can apply a lower voltage that will result in a higher field on the material. And this is very interesting for an actuator application. You reduce the operating voltage. We are talking 60 to 200 volts. So it is still reasonably high voltage, but it's much lower than the equivalent of with the bulk component. At the same time, you can apply a higher field on the material. That means more electrical stress that results into higher strain. And also you encapsulate, so the active material is surrounded by inactive material that acts as the protection against the environment. We can also play with multiple functions. So we've made actuators a combination with sensors, for example. So you have a few layers that are connected separately that are used as a sensor. Or we have also made some other devices with several active regions in them. There was one for adaptive optics, for example. There was a bar with, I think, 10 regions that could be addressed separately or individually. Okay, moving on to the modes of operation. If you've seen the previous webinar, you know that we have what we call the D33, which is the response in the polling direction. We also have D31, which is the reaction across so perpendicular to the polling direction. And you can actually use both for actuator applications. You can also use the D15, which is the shear response of the device. So when you apply a field that is perpendicular to the polling direction, then you have a shear motion of the device and the top electrode. Briefly through the principles, because I think we're rapidly running out of time. We manufacture actuators in single components that are typically 2 millimeters thick and that provide around 3 microns of displacement. And all this can be customized, of course. If more displacement is needed, our approach is to stack several of these individual components. That gives us more flexibility. Some other manufacturers will just manufacture a single stack, but then they have to deal with this issue that I mentioned before with the strain on the inactive regions, and they have to deal with that, or they deal with that in different ways. But we have here this option to stack and get much higher free displacement. It says here up to 250 microns. That's actually a little bit high. So we don't actually make that many stacks that give very high displacement like that. Usually we're talking about smaller stacks like this that give 20, 50 microns. It's very popular for positioning applications. The stack can be preloaded like here, or encapsulated like here to protect them from the environment or cool them down. I'll just let you refer to the different options. To move on to amplified actuators, so when more displacement is required, very often we use an amplification mechanism. This is used on AFM tables, for example. If you have a table with a displacement of 500 microns, then it's typically a 50 micron actuator that is amplified with a factor of 10. There are different ways of amplifying. The most simple way is to use just a flexure and a lever effect. It looks very simple, but it's actually what's most commonly used for positioning, nano positioning applications. So here with an amplified actuator, you trade off some of the force capability for more displacement. So obviously, when you add material and add the amplification, you reduce the stiffness, but you gain in terms of displacement. So there is nothing comes for free, right? Bending actuators, here we're moving to D31 type. So you use the contraction in D31 by applying placing the piezo on a substrate, which can be different materials. When you contract the piezo, so you increase the voltage, it will contract in D31, and since it's constrained against the substrate, it will tend to generate a bending motion. And you can do that with piezo on one side or on both sides. And yeah, it's typically a thin piezo, so very low stiffness, but large displacement. We do the same with multi-layer components, except that for multi-layer, at least in our design, we don't use any adhesive or substrate. We define 2 sections within the ceramic body by alternating the electrodes in a specific way. So we can contract just the top section or the bottom section. and that generates the motion. And we can do that either in a plate or in a ring shape. The plates will provide higher displacement, the rings will provide higher force. Shear elements are very straightforward, so I'll just go briefly through that. Single elements provide displacement in the micrometer range, and when we stack them, we can go up to, well, several microns, but we can, most interestingly, we can make XY or XYZ motion. So if I plot, we've defined the free stroke and blocking force previously. So if I plot the different designs here on the free stroke and blocking force diagram, you can see the single tiles here in the micron range, but very high force. When we stack them, we increase the displacement, but keep the force capability. And when we amplify them, we actually shift. So we're getting a certain factor in displacement, but we also decrease the force capability. And then we have benders here, which are somewhat more flexible. So higher force, but higher displacement, but lower force. 3 minutes. That would be interesting. Now, how to choose? We've seen the different designs. You have to know your load, and you need to find a design that contains your load, basically. So again, I have to go a little bit briefly through this part. There are some dynamic aspects which I won't have time to cover here. But starting with the static aspects, you have to find the best fit for your design. And then there are some optimization parameters. So what's important for you? Do you need to minimize a certain dimension? Do you need to minimize mass? Do you need to minimize cost? This is something that you need to be clear about from the beginning. One last thing that I want to cover, that I still have time to cover today, is the load matching principle. So we've talked about force displacement, and I mentioned that you always get a combination of force and displacement. You don't get unless you have a constant load. So with the spring load, you get a combination. And if you look at this graph here, if you have a very soft spring, so piezo pushing a very soft spring, you generate a large displacement, but a very low force. So in the end, the energy transfer, which is the product of force and displacement, is actually relatively low. And when you have, on the opposite side, if you have something that is very stiff, then the piezo will push as hard as it can, but it won't be able to generate much displacement. So here again, the energy transfer is very low. And it turns out the best energy transfer is when the stiffnesses are matched, so are similar between the load and the actuator. So this is where you can transfer the energy in the most efficient way, and that minimizes your volume and also the cost. But you can have reasons for not matching the load. You can have to, for example, increase the bandwidth. So if you need a fast response, then you will need more force than just the static value. You can need some margin for some of the nonlinear aspects. For example, temperature range. If you need to make sure that you can cover the load over a wide temperature, then you will need a larger device. There's more about dynamic applications, but I don't think I have time, so I'll just browse briefly through the summary. There are some different designs. We can interesting. We have faster, smaller devices for fast response, and a wide range of actuators. So if you're ever in doubt, please contact us, and we'll be able to help with your design, including the dynamic aspects that I haven't had time to cover today. But that was it for the webinar. I'm sorry I'm running out of time, but we got some very interesting questions. So thank you all for participating and for your interesting questions. I might come back one day for more information and maybe a second session. We'll see. In any case, thank you.